HW12 Question 1, Part C. Here we have a very interesting equation. We'll assign oxidation states to all elements within all species, and then we'll see something kind of funny happen. Let's start with the easy ones. When lead is alone and neutral, it has an oxidation state of 0. Within lead 4 oxide, this one's not too hard, but we'll work through it anyway. -2 for oxygen. Lead's charge, well, you know what, you could just say, hey, it's got to be lead 4 ion. Lead 4 ion, when paired with oxide ion, is what would make it balance. So here we have +4, so +4 -2. Within sulfuric acid, H2SO4, we have the sulfate ion, which is SO4 2-, and 2 hydrogen ions, which are +1 in charge. So hydrogen takes a +1, and in the sulfate ion, since oxygen is more electronegative than sulfur, it'll take the -2 charge. Sulfur will take whatever charge is needed so that the oxidation states add up to the overall charge of the species, which is -2. Let's do a little math. 1 atom of sulfur, whose oxidation state is not known, when added together with the 4 atoms of oxygen, whose oxidation state is known to be -2, should equal the overall charge of -2. We'll add 8 to both sides, and we find that sulfur's oxidation state would have to be +6 in this compound. So let's record that up above. Hydrogen's oxidation state +1, sulfur's +6. Let me move that over just a smidge. And oxygen's would be a -2 within sulfate ion. For lead 2 sulfate, we also see the sulfate ion. Let's identify those ions, lead 2 and sulfate. And students, I'll give you a hint. Once you've figured out the oxidation states for the elements within the sulfate ion, you've got it for life. So if you figured out earlier that sulfur was +6 and oxygen is -2, then that'll be the case every time you see sulfate. So without even having to redo it, let's throw in a +6 and a -2. Lead, in the case of lead 2 ion, is alone and it bears a charge. So that charge is its oxidation state. Let's record that. So, what was oxidized and what was reduced? Something very interesting happens here. First of all, sulfur's oxidation state of +6 on the left side matches what we see on the right side of +6. Oxygen's oxidation state of -2, both in PbO2 and in SO4, matches what we see on the right side with a -2. But something really interesting happens with lead. In the case of Pb becoming PbSO4, it went from an oxidation state of 2 from 0 up to +2. And in the case of PbO2, it went from +4 down to +2. Crazy. Lead is both oxidized and reduced. The same element goes both ways in this equation. Let's record this. This is really an interesting one. We don't see this often, but this is a fascinating problem where we get to see a single element doing everything. So, starting with the oxidation half reaction. The species oxidized was neutral lead, and it became, on the right side, lead with a 2+ charge within lead sulfate. Now, I understand why you might be confused here. You do need to carry through the sulfuric acid in order to make the elements balance within this half reaction. So, let's apply our steps of redox balancing. Step 1. Balance elements other than H and O. Well, we have one lead atom on each side of the equation and one sulfur atom, so it's already balanced. Step 2. Balance oxygen using water. We have 4 oxygen atoms on either side, already balanced. Step 3. Balance hydrogen atoms by adding hydrogen ions. Well, we have 2 hydrogen atoms within sulfuric acid, so we needed to add 2 hydrogen ions to the right side. Step 4. Balance charge using electrons. On the left side we have 2 species which are neutral, and on the right side we have a neutral species and 2 species which are single positive. That means its charge on the right side is a +2. In order to make the charges match on either side of the equation, we can only reduce the charge by adding electrons. There's no way to increase the charge. So on the side where we have a +2 charge, we're going to knock the charge down by adding 2 electrons, and that brings it down to 0, which is a match between the left and right sides of the equation. The other half reaction, the reduction one, also involves lead. This time, it's the lead within lead 4 oxide, the PbO2. We also need, in this half reaction, sulfuric acid, because sulfate ion appears in lead 2 sulfate. So we need, and we can use it in both half reactions. It's okay to do this. Step 1 for balancing half reactions. Balance elements other than H and O. We have 1 lead atom on each side. That's balanced. We have 1 sulfur atom on each side. That's balanced. Step 2. Balance oxygen using water molecules. Here we need some balancing. We've got 2 oxygens within lead 4 oxide, plus another 4 within sulfuric acid, and we only have 4 within lead 2 sulfate on the right side. So we need an additional 2 oxygen atoms, which we can find in water, and that needs to be added to the right side. Upon doing that, we've thrown off our hydrogen count. We have 2 hydrogen atoms on the left side within sulfuric acid. We have 4 hydrogen atoms on the right side within the 2 water molecules. So to make it match, we add an additional 2 hydrogen atoms on the left side. Step 4. Balance charge using electrons. Let's count up the charge on both sides of the equation. On the left side we have 2 species which are single positive in charge, 1 species that's neutral in charge, another species that's neutral in charge. Altogether, that's +2. On the right side of the equation, 1 species that's neutral in charge, 2 species that are also neutral in charge. Overall, that's neutral. To make the charges match, we can only reduce the charge by adding electrons. So we'll add 2 electrons to the left side, and by doing that, we've knocked the charge down to 0 on the left side, which matches what you find on the right side, and we're good. Next, we add the 2 half reactions together. Thankfully, in this equation, we don't need to multiply coefficients. We have 2 electrons lost in the oxidation half reaction and 2 electrons gained in the reduction half reaction, the number of electrons already matches, so we don't need to do anything on that front. Let's simply rewrite the 2 half reactions and we'll add them together. And we'll add those 2 equations together, making sure that the number of electrons crosses out. That's of crucial importance. But beyond just crossing out the electrons, we can also cross out the hydrogen ions. And when we add these together, we'll combine the sulfuric acids and the lead 2 sulfates. So on the left side we have 2 sulfuric acid molecules, and on the right side we have 2 lead 2 sulfates. This was a tricky one. Hope you enjoyed it.